Today we are going to study the quantum numbers associated with vector atom model. In the last class we have studied the vector atom model, and the two main concepts of vector atom model are the spatial quantization and the spinning of electron. And the vector atom model is an atom model in terms of angular momentum, and it is an extension to the Bohr-Sommerfeld atom model to the multi-electron system. And the main outcome of the vector atom model is the introduction of quantum numbers. And the quantum numbers associated with the vector atom model are, first one is the principal quantum number and the orbital quantum number, spin quantum number, the total angular momentum quantum number, the magnetic orbital quantum number, the magnetic spin quantum number, and the magnetic total angular momentum quantum number. The principal quantum number n, it represents the principal orbit in which the electron belongs, and it is identical with the one used in Bohr-Sommerfeld theory. And this principal quantum number, it is represented by n, and it takes only integral values excluding 0. And the angular momentum of the electron in an orbit is given by nh divided by 2 pi, where n is an integer excluding 0. If n is equal to 1, it means the electron belongs to the first orbit, and if n is equal to 2, it represents that electron belongs to the second orbit. That is, the principal quantum number n represents the orbit in which an electron belongs. And second is the orbital quantum number, and is represented by L. And this quantum number defines the shape of the orbit occupied by the electron and the angular momentum of the electron. It takes all integral values from 0 to n minus 1. That is, if n is equal to 2, then L can have value from 0 to n minus 1. That is 0 and 1. That is, the value of the orbital quantum number L depends on the value of the principal quantum number n. This orbital quantum number L refers to an energy subshell. That is, if L is equal to 0, that orbit is called s orbital. And if L is equal to 1, it is called p orbital. If L is equal to 2, it is called d orbit. If L is equal to 3, it is called an f orbit. And the orbital angular momentum of the electron is given by LH divided by 2 pi. Third is the spin quantum number, and is represented by S. In an atom, the electron which is revolving around the nucleus in an orbit, at the same time it spins about its own axis, and this spinning of this electron is represented by a spin quantum number, and this magnitude is always half because electron is a spin half particle. Since the electron can spin in clockwise or anti-clockwise directions, this S can have two values, that is plus half or minus half. That is, the plus half values indicates a clockwise spin represented by an arrow pointing upward, and the minus half spin indicates an anticlockwise spin represented by an arrow pointing downwards. The spin angular momentum is represented by SH divided by 2 pi. Next is the total angular momentum quantum number, and is represented by the letter J. This total angular momentum quantum number can be represented as the vector sum of the electron's orbital and spin angular momentum. That is, if L represents the orbital angular momentum and S represents the spin angular momentum, then the total angular momentum J can be represented as L plus S, or L minus S. This L plus S value means both L and S are in the same direction, and L minus S values represents both L and S are in the opposite direction. The total angular momentum can be represented as JH divided by 2 pi. And next is the magnetic orbital quantum number. And this magnetic orbital quantum number represents the influence of an atom under the action of an external magnetic field. Because when an atom is placed in an external magnetic field, then the orbital quantum number L, it just precedes about the direction of the magnetic field, and this precision is called Lamer precision. And this magnetic orbital quantum number, it can be represented by ml, and this ml can be represented as the projection of the orbital quantum number L on the magnetic field direction. Since the projection is also quantized, ml can have only integral values, that is L, L minus 1, L minus 2, etc. plus L2 minus L. That is, there are a total of 12 plus 1 possible values for the magnetic orbital quantum number ml. Here, the angle theta is an angle between the L vector and the B vector. Here we can represent it as magnetic field. That is, here this L vector can be represented, and the ml vector can be represented as the projection of this L vector on the field direction, and this is the projection. Therefore, the ml can be represented as the projection of the L vector along the field direction. And this ml can have values from minus L to plus L, or it can have a total of 12 plus 1 values. For example, if L is equal to 2, then the ml can have values from minus L to plus L, means minus 2 to plus 2. That is minus 2, minus 1, 0, plus 1, plus 2. That is, there are a total of 5 values. That is, there are 12 plus 1 values. That is 2 into L is equal to 2, 2 into 2 plus 1, that is 5 values. That is, if L is equal to 2, the permitted orientation of L are 5, for which the ml can have values 2, 1, 0, minus 1, minus 2. That is, the L vector can have only 5 directions, and that is called the spatial quantization. That is, corresponding to L is equal to 2 value, the ml can have only 5 orientations. That is, the orientation of this orbit is restricted to only 5. 5 orientation ഇവിടെ possible ആവുന്നുള്ളൂ. അതുകൊണ്ട് ഈ 5 orientation മാത്രമേ ഈ ഓർബിറ്റിന് ഓറിയന്റ് ചെയ്യാൻ പറ്റൂ. അതിനെയാണ് spatial quantization എന്ന് പറയുന്നത്. That is, here both the L vector and the projection of the L vector on the field direction, that is the ml, both L vector and ml vector are quantized. That is called spatial quantization. And the 5 orientation can be shown in the figure, and this is the one orientation for ml is equal to 2, and this is another one orientation, and this is another one orientation, this is another, and this is another one orientation. Only 5 possible orientations are permitted. And for L is equal to 3, the permitted orientation of L are 2L plus 1, that is 2 into 3 plus 1, that is 7 orientations. And the ml values are minus L to plus L, that is minus 3 to plus 3. That is 3, 2, 1, 0, minus 1, minus 2, minus 3. That is, here only 7 orientations are possible. The 7 orientations can be represented in the figure. That is, this is one orientation corresponding to ml is equal to plus 3. This is another orientation which is corresponding to ml is equal to plus 2, another one corresponding to ml is equal to plus 1. This is 0 and this is corresponds to ml is equal to minus 1. It corresponds to ml is equal to minus 2 and this corresponds to ml is equal to minus 3. That is, this is the spatial quantization. Next is the magnetic spin quantum number ms. And this magnetic spin quantum number is the projection of the spin quantum number s along the direction of the magnetic field. Since the value of the s is always half, the ms can take only two values, plus half and minus half. Next is the total magnetic angular momentum quantum number. It can be represented as mj. And this magnetic total angular momentum quantum number can be represented as the projection of the total angular momentum vector j on the field direction. And this j can have half integral values because j is equal to L plus or minus s, and depending on whether L and S are both in the same direction or in the opposite direction. Therefore, the mj can have only half integral values. The possible values of j are minus j2 plus j excluding 0, or total 2j plus 1 values excluding 0. For example, if L is equal to 2 and S is equal to plus half. If L is equal to 2 and S equal to plus half, then j will be 2 and a half. Then j can have total 2j plus 1 values, that is 2 into 2 and a half plus 1, that is a total of 6 values. That is total 6 values, and the values are 2 and a half, 2 and a half minus 1, that is 1 and a half, then 1 and a half minus 1, that is half, then half minus 1, that is minus half, then minus 1 and a half and minus 2 and a half. That is total 6 values are possible excluding 0. That is, the magnetic total angular momentum quantum number mj can be represented as the projection of the total angular momentum vector on the field direction, and this j can have integral value, half integral values, and the possible values of j are minus j2 plus j excluding 0, or total 2j plus 1 values. And these all are the main quantum numbers associated with the vector atom model.